Okay, so welcome back to another video. So in today's video we have yet another integral, the integral from 0 to 1 of the fractional of 1 divided by the kth root of x dx. And I should also mention that we have our little k, so this only works for all k that are in the natural numbers excluding the singleton element 1. So, okay, that's our little condition that we want to satisfy. And then now we're just being asked to find the integral. And in case you haven't noticed, if you're new to this channel, if you've never seen a fractional, then I've used this several times before, but fractionals are usually defined as the following. So it's a fractional of x is actually equal to the integer x, and then subtract that with the floor of x, where the floor of x is basically the greatest integer less than that. With these little definitions here, then we can actually rewrite some things and then be able to calculate and simplify our given integral from there. With that, let's start off by actually doing a u substitution. So I'm going to let u equals the inside of our fractional 1 divided by the kth root of x. Obviously we're going to have to do some substitution, but what I'd like to do is I'd like to rewrite this in terms of x. So when I solve for x, so that means I will get that this is x is equal to 1 over u to the k power. And so from there I'll differentiate both sides of dx and get du. So du is equal to, or what I meant to say is dx, because we're differentiating both sides of this part here. So dx is equal to, let's see, the derivative of 1 to the 1 divided by u power k, so that will be negative k, and then divide that by u to the power k plus 1, and then dx. Okay, or du. I'm getting those terms mixed up. And now from here, let's actually change our bounds of integration. So we're given x is equal to 0, and then x is equal to 1. And so what that implies is that as x is equal to 0, then that would have to mean that u would have to approach infinity, or rather we could say u is equal to infinity. And then for x is equal to 1, then u would have to equal 1 as well. So now let's actually rewrite our integral. So I'm just going to rewrite our given again. So the integral from 0 to 1 of our fractional 1 divided by the kth root of x dx. And now if we substitute our pieces, then we will get that this is the integral from from infinity to 1 of the fractional of u, and then multiply with our dx substitution. So then this is negative k, and then we divide this by u to the k plus 1, then du. Obviously I would need to change the bounds of integration because we have an infinity that's in the lower bound and then one that's the upper bound. Obviously you can't do that. So what this means is that I'll change the order of integration, but that means that the whole integral will become negative, but we have our negative from our dx substitution, so that will cancel. And we also have a k that's a constant as well. It does not depend on our variable u, so I can simply just move that outside of the integral. So now we have k. Also, I think my red marker is kind of running out of, it's almost running out, so I'm gonna have to discard that soon. So I'll just switch to orange. So now we have that this is k, and then multiply with our integral from 1 to infinity of the fractional of u, and then we divide this by u to the power k plus 1 du. And so you get the idea about the fractionals. So we said that the fractional is equal to some integer x minus the floor of x. So what we can do is we can actually break up this integral into infinite sums of small integrals with those integer limits. And so what that implies is that we're going to write this as a form of an infinite sum of the integrals. So let's see, going from this step, so that means this will be some constant k, and then multiply with our infinite sum. So this is going from n is equal to 1 to infinity of our bounds, which starts from n to n plus 1 of, so far this is just the fractional of u, and then divide that with u to the k plus 1 du. All right, and you'll see that we have to start with one step at a time, so that means we start with n is equal to 1, so we go to we integrate from 1 to 2, and then we add this with our next term 2, so 2 to 3, then 3 to 4, and then 3 to 5. But what that also means is that I'll have to replace this the fractional u with our definition of what it is, x minus the floor of x, or in this case u minus the floor of u. And so what that implies is that every single time we evaluate between each of those limits from for our bounds from 1 to 2, no matter whatever number is in between those intervals for each terms we we put in and then add to those sums, it's always going to be its floor is always going to be the always going to be equal to the lower limit of the bound. So we have that. Let's say for example we integrate this from 1 to 2, and if we plug u minus the floor of u for that bound between 1 to u, then you'll notice that in between that bounds, the floor of in between that, it's always going to be 1. So that means when I replace, so here, let's actually do that substitution first. So 1 to infinity, so u, okay. I'm just gonna rewrite this again a second time. So what that means is I'll replace this, I'm supposed to write a sum here, so give me a second to rewrite that. Okay, so then now if I replace this, we'll get, let's see, the same infinite sum. And so we replace this with u minus the floor of u, and then u to the power k plus 1 du. Okay, and that's all good and dandy. And so every time we plug between each of those limits, I can just replace that with the floor of u is equal to n, for we're adding all the terms of n, as this is an infinite sum. So then right here is k, then we have our infinite sum from our bounds from n to n plus 1 of u minus n, and then divide that with u to the power k plus 1 du. Okay, and so I can break this fraction up together since they share the same denominator. So then this is basically we're splitting this up into two integrals. Well, we'll get to that step. Let me just write this under one integral for now before I skip some steps. Well, not really skip a step, but before I write the next steps. So n, then n plus 1. And so really we have u to the divided by u to the k plus 1, and I subtract that with n divided by u to the k plus 1 du, and now we can actually perform the necessary definite integration. When I do this, then let me just write over here. So this means we have, this is k, and then now we have our infinite sum, n is equal to 1 of, so this will be u to the negative k plus 1, and then we divide this by negative k plus 1. Then I subtract this, so there's an n over here, so I'll just factor this outside. And then when I integrate this is basically the integral from 1 divided by u to the power k plus 1. So I'll get that this is u to the power negative k, and then I divide this by negative k. Okay, and then now from here is that I can actually integrate our bounds from n to n plus 1. All right, so now I can actually plug our stuff in, k, and then infinite sum. We're just rewriting things again. So now the next part is now plugging in our bounds into here. So then let's see, plugging in the n plus 1 into here, then this should be, let's see, negative n plus 1 to the negative k plus 1, and then divide by negative k plus 1. And I subtract that, so, well, not yet. This is still part of the integrating or putting our bounds for n plus 1. So n plus 1 to the negative k, and then divide that by negative k. So that's first. So now I have to plug in n. So then this is, subtract that with, let's see, so this is n to the negative k plus 1 divided by, well, I think I missed an extra parentheses, so. Actually, no, I'm not. I was right. This is supposed to be, actually, yes I am. So here, n negative k plus 1, and I divide that by negative k plus 1, and then subtract that with n, then multiply with n to the negative k. Looks like an h. Sec n negative k, then divided by negative k here, and then I'll close this bracket. Okay, let's actually rearrange some terms from here, because otherwise, from then doing this, we can actually simplify some stuff out. So let's see. So let's see k, then back we go with our infinite sum. Now here's the part that we're gonna rearrange. So n plus 1, so this part still stays the same. And I divide that with negative k plus 1. And then now I subtract this with, so I'll move back the n over here, or actually this is supposed to be, this is still n times. So because everything here is just commutative, so this should be fine to do this. So then this is n negative k plus 1, then divided by negative k plus 1. Actually, there should be an n over here because n is multiplied by here. Really, k plus 1 and then negative k plus 1. Now from here is, now subtract this, and then n is being multiplied with everything here. So this is n plus 1 to the negative k, and then divide this with negative k. And now subtract this with n, and then negative k divided by negative k. Now I can do even more further simplification. So let's see, k, and then back to our infinite sum notation. What I'll do is I can actually factor out a negative, or 1 divided by negative k plus 1 outside from these two terms here. So let's see, 1, then negative k plus 1. I know I can just write the negative on the top, but we don't want to do that just yet. So this is simply just for the sake of making things easier for us to simplify. We're having to go a few steps further ahead. And so I can rewrite the exponents from here. Negative k plus 1 is the same thing as 1 divided by n plus 1 to the power k minus 1. Okay, and then over here, do the same thing. So let's say just subtract that, and then this will be 1 divided by n k minus 1. Now from here is that I can actually factor out negative k, and so with the n over here, and then there's negative, so this can change to a positive, so this is n divided by k, and then multiply with, so this is 1 divided by n plus 1 k, and then over here is that's supposed to be minus, so this will be 1 divided by n to the k. Okay, and then now I'll just factor out the negative k plus 1 from over here. Well, and then really I'm going to break this up into two sums, a sum of the infinite sum. So we have the infinite sum corresponding with here, and then another infinite sum corresponding with this term. But likely here that I'll actually factor out the negative k 1 over negative k plus 1. Really, I can just factor out the k minus. So that'll actually just become a k divided by k minus 1 from specifically I just multiply the negative. Okay, let me retracting from what I said. This became a k divided by k minus 1 simply because not only did I factor out the negative k plus 1 back out to here, but I also rearranged the terms. I'm going to rearrange the terms, so this will come first and then this will come second. But really, this will factor out the negative, and then eventually this will become a minus. So really the terms have been rearranged, factor out the negative, and then we can actually just rewrite our constants from out here. Okay, so then minus, and then n plus 1, and then k minus 1. N plus 1, k minus 1. Okay, now from over here, I can just distribute the k times this infinite sum to here, then the k's will cancel, so this will simply just become the infinite sum. N is equal to 1, and then infinity, then n times, since the sum depends on our terms of n, then this still stays the same. So this is just 1 divided by n plus 1, k, subtract that with 1 divided by n to the power k. And so if you notice closely, this infinite sum and then 1 over n times some exponent is actually in the form of a Riemann zeta function. So I can actually rewrite that. Same thing from over here, but it's going to be a little bit different. Let's see, so a Riemann zeta for this can be written as this this is simply just the Riemann zeta of k minus 1. And now let's subtract that with over here. This is going to be a rewritten expression of k minus 1. Then the explicit formula, how it's defined, really is going to be written as the Riemann zeta k minus 1, and then add a 1 to that, or subtract a 1, that's what I meant. Now from here, I'll just distribute the n into the inside of those expressions. So n equals 1, and then see n divided by n plus 1 to the k, and then minus n divided by n to the k. And well, really, I can also write this in another exponent. So really, I can move that n into the, where am I putting it? I can move that n after I distribute back to the denominator. So really, this will just be 1 divided by n to the power k, and then minus 1. And now from here, now further simplification, let's see, Riemann zeta k minus 1 and minus that cancel, so we add a 1. So that means this whole expression over here is simply just k divided by k minus 1. Okay, and now all that's left is to evaluate this sum over here. So what I'm going to do from here is, specifically this term, I'm going to add and subtract a 1. So let me first write out the infinite sum here's notation. And then this will be n, then minus 1, and then plus 1. Better, let me just write plus 1 first, and then minus 1. 1 minus 1 being divided by n plus 1 to the power k. And then this is will still remain intact, k minus 1. So what that implies is that I can actually rewrite split this into fractions over here. So now we have, okay, so k and then k minus 1 plus infinite sum, n is equal to 1. And so from here, this will be, let's see, the terms cancel from, well, it's not really the terms cancel, but really n plus 1 can move into the denominator, just like what I did with that similar argument. This time, this can be rewritten as 1 divided by n plus 1 and then to the power k minus 1. And then over here, we have a negative 1, so subtract that with 1 to minus n plus 1 to the k. And then this will still remain the same, minus 1 divided by n to the power k minus 1. Well, and then now I can actually from here just switch our terms. So really, minus 1 over k minus 1. Here, let me actually just do that now. So this, I'm just moving terms. So this is supposed to be n k minus 1, and I'll subtract that from over here, and then this is 1 divided by n plus 1 to the power k. And now from here, I'll just again use our Riemann zeta function since they have the similar notations. Let's see, this is plus, and then we have that our first term over here. This is, let's see, 1 and then n plus 1. So this can be written as Riemann zeta k minus 1. It's simply just the same thing from where is it? This was from earlier, right over here. So that's just Riemann zeta 1 minus 1. Okay, and then now subtract that with, now this is also Riemann zeta, so this is Riemann zeta of k minus 1. And then over here, we still have that sum to evaluate. So this we have the infinite sum of, let's see, this is minus, so, well, actually, it's still fine because it's a minus, so, but yeah, it is sum. Okay, and then 1 divided by n plus 1 to the k. So we just performed the necessary algebra from here. Then you're gonna see that these two cancels, and then we're just left with a minus 1. So then k divided by k minus 1, subtract that with 1, and then subtract that with our infinite sum of 1 divided by n plus 1 to the power k. And so the last step is that minus 1 minus the infinite sum of 1 over n plus 1 to the k. What I can do is I can actually change our index. So this time I'm gonna let n equals 0. So if I were to do that, n is equal to 0, so evaluate this and n equals 0, so it's 1 divided by 0 plus 1 is 1 to k, so that we get that this is a negative. Really, we have the same thing from over here, so really this negative 1 can just go back into our sum from over here, but our index will change. So really, this is k divided by k minus 1, and then subtract this with our infinite sum starting at n is equal to 0 of 1 divided by n plus 1 to the power k. And then if you see that I actually just changed the index again a second time, and so you'll see that this is actually just rewriting the zeta function at k. So therefore, we come to the conclusion that this is k minus 1, and then subtract this with our Riemann zeta of k. And there we have it. That's the final answer concludes in this black box. And I'm dropping markers everywhere. That's pretty nice. All right then. Now, that's pretty cool if you ask me.